Hello students, we were discussing the direct sequence spread spectrum communications, and in this module we will continue that discussion, and in this module we are mainly focusing on the fact that we understand direct sequence spread spectrum system. Any spread spectrum system in that sense was designed to give a resilient against the jamming environment. We have also discussed in the last module about the processing gain, and we saw that it is a measurement which can give you how much resilient you are, how much resilient, by what factor you can have the resilience against the jamming environment. But apart from the processing gain, there is another term used in the system design which is called a jamming margin. Today we will also try to concentrate about this jamming margin. We will try to get the concept of jamming margin, and we will try to see what is the typical relation between this jamming margin and the processing gain. See, this jamming margin, it is the level of the interference that a system is able to accept. So, if I tell you the jamming margin is, again it is expressed in dB, it is this much dB. That means from the system design perspective, it is the amount of the dB level where actually any amount of the interference, straightforward it says the amount of the interference that the receiver can withstand. And withstand, it means withstand with the specified level of the performance without actually diminishing the quality of the error performance or diminishing the value of the bit error rate. This is the extra amount of the interference it can accommodate, such as to maintain its bit error rate ratio, exactly what you are getting. So, without compromising any error increment or decrement in the signal to noise ratio, the extra amount of the interference power that it can accommodate. The jamming margin usually is considered as the jamming power to the signal power. It is a figure of merit, and that provides a measure that how vulnerable your system is to interference. And obviously, we would like to have a larger value of the J by S, and because it is system is the greater is the system is to the interference part, resistance to the interference part, it forces to employ a greater processing gain. Remember, if you wish to get higher resilience, this factor needs to be higher, which finally boils down to the fact that you have to have a higher processing gain. If you wish to have a higher processing gain, then the Ts by Tc, that ratio, it needs to be high. In order to make this high, you have to decrease the value of the Tc, keeping the same, considering that the simple duration we are not changing. So, you have to decrease the value of the Tc. Once I am decreasing the value of the Tc, hence the length of the sequence that I am dealing with, that is increasing. So, you are boiling down to the fact that you are increasing very long length sequence for the spreading, which has lot of its own kind of disadvantage as well as advantage in the practice, but the relation is something like this. Though the processing gain is having some direct relation with the interference rejection properties, as we have discussed in the last module, but remember that there are some few more factors which relates the processing gain with the jamming margin. If I tell that the jamming margin is given by my Mj, then and Gp is my processing gain, then processing gain subtracted by the minimum required Eb by N naught at the output, and it depends, the requirement depends on the kind of the modulation you are utilizing. Definitely, if you go for a higher modulation scheme, S by N requirement at the output will keep on increasing, and L system talks about the amount of the losses that can happen once you go to implement the system. So, considering these two EB value, these two dB values, the subtracted value of this summation from the processing gain will tell you what is the jamming margin you are left with. For example, I have a spread spectrum system with this processing gain is equal to 30 dB, where 3 dB is the loss in the system, and 10 dB is the required SNR output for a typical kind of the modulation system. Then you will be ending up with the 17 dB of the jamming margin. That means the system can work nicely up to the interference power level go as high as 17 dB above the desired signal. But beyond that, in that the environment where the jamming power goes 17 dB, beyond 17 dB above the signal power level, the design system cannot work. This is the meaning. So, today we will also have the mathematical analysis. We will do the mathematical analysis to understand in detail the relationship between this processing gain, jamming margin, how it does it, do they look like. Some further, before going detail in that, we would like to revisit the fundamentals of the digital communication system, because a lot of understanding we need to revisit before entering into the spread spectrum communication system analysis. Figure 1, we have shown digital communication system model. See, a digital communication system starts with a message source. Let us assume that this message source is generating the messages MIs, where I can go from 1 to capital M. So, as if I have a set capital M who is having the number of the message symbols who is running from M1 to capital M, and this is we call it is an alphabet also. And this message source, in each of these messages of this alphabet is called a symbol, and each of these symbol is having a duration of t seconds. And moreover, we are thinking that this message source is drawing randomly one of these symbols from this set, and he is transmitting and sending to the vector transmitter. And we also assume that a priori we know the probability associated of assigning each symbol to the vector transmitter, and that probability, all the probability of getting any one of these symbol values from this set are equal, and hence the probability of pi associated with the ith symbol of choosing that typical symbol is equal to 1 by capital M. The selected message symbol is sent to the vector transmitter. The task of this vector transmitter is he will actually for every real valued signal he will develop some vector symbol, and he at the output of this vector transmitter, hence for every MI we will be able to see a vector representation of this MI which is given by SI. How SI looks like, let us see in the next PPT, in the next slide. SI is a vector, so it is written in the bold, and it combines actually the for every ith sample it has capital N numbers of the vectors. So, for each and every symbol it has a linear combination of capital N number of the vectors. It generates actually the, and you can actually have a recursive signal SIT that is generated at the output of the vector, that output of this vector messenger or the vector transmitter, where actually this SIT is the combination of the multiple number of this vectors which is drawn from this capital, it's drawn from this SI. And remember the constitution of this SIT is such that, and over the duration of this capital T, the total energy of this SI will be normalized to 1, and SI can vary for over the symbol. So, hence it can have, I can go for 1 to capital M, and it will get, you will get the signals S1 to Sm. So, one of the real valued such signals, once this signal is constituted by the linear combination of these vectors, and any one of those real valued signal now will be transmitted over the duration of capital T over air. And which one will be transmitted, it is based on the incoming messages, and also it depends on the message transmitted in the last time duration. The transmission that will be done, it is on the air, and hence we need to look little bit about what kind of the channel, wireless channel we are looking about. See, the output of this SI is now getting modulated by the modulator, and you have constructed the SIT, and now it is released to the channel. So, for our understanding, we will consider a channel who will have at least the bandwidth equal to the signal bandwidth or more than that. And we are also considering that the noise that is getting added from the channel will be additive wide Gaussian noise process, and that noise process we will be now mentioning as WT. Okay. And hence the transmitted signal SIT that the modulating block is giving you, that will be now distorted by this additive wide Gaussian noise process. If I try to depict it in a figure, see the figure number 2 is taking the signal from the output of this modulator, and the channel is adding the noise, remember, and generating the signal. This is xt is the received signal. Remember, actually WT and xt, they are the sample value of this random process capital XT and the capital WT. And from now onwards, this xt will be considered as the received signal for us. And receiver will now have the information about xt. Once observing the value of xt over the duration of capital T, of course, the task of the receiver is to estimate the value of this Mi. So, he is having a received signal contaminated by the noise, and based on that received observation, his task is to estimate the what was the transmitted signal Mi. Receiver does this job into two halves. In the first process, there is a detector who works or operates on that random process xt, received random process xt, and he generates a vector of the random variables, which is capital X. And now, by observing the small x, which is a random sample value of this capital X, with the prior knowledge of this SI, I mean the vector transformation done in the transmitter, with the probability of occurrence of all those samples probabilities Pi, and this vector receiver generator is now trying to estimate the value of Mi. So, one is the detector and second is the decision device and the estimator cum decision device, who combinedly work to estimate the value of Mi in the receiver. So, this is a normal receiver architecture that we deal with the digital communication system. And remember that receiver can do the occasional errors, because wide Gaussian noise is present and noise is completely random in nature, and error probability will be defined if we see that estimated value of M is not matching what was transmitted from the transmitter. This architecture what we have discussed right now, this gives at optimum receiver design, in the sense that the error probability will be minimized. And in that, the general assumption that we have done in this discussion, that transmitter and receiver are well time synchronized. That means receiver understands at what moment Mi changes. Also, if we are having an understanding that receiver is completely phase locked with the transmitter, then we call that receiver is a coherent receiver, and if the receiver is not phase locked with the transmitter, we will call that kind of receiver is a non-coherent receiver. And this model provides a very basic assumption of the optimum receiver design, but we wish to zoom inside the graphical representation and inside the graphical representation of this transmitted signal SIT, because this graphical representation of SIT will be very much important for us to analyze our direct sequence spread spectrum transmitter receiver. So, now onwards we are zooming inside this SIT and trying to see the geometrical representation of this SIT. Very famous method of having a geometrical representation of this SIT is the Graham-Smith orthogonalization procedure, which will be discussed next. This orthogonalization procedure is basically telling the method how will you present capital M energy signals, SIT as some linear combination of capital N orthonormal basis functions. We have seen in the vector transformation that we are having capital N dimension for each and every ith symbol that is coming from the message source, and we saw also that inside the vector transformation representation, the value of the capital N chosen, it is less than equal to the total number of the symbols present in the alphabet set. So, N will conformly it should be less than equal to capital M. Now, we are having a set of some real valued energy signals. So, it is varying from the S1 to capital M, because that we have started with capital M is having the values of this S1 to your SM. Capital M was a set of SM. So, here it is not the M, here it will be the value of capital S, where actually S is now S1T to varying up to capital SMT, where M was actually related to the message bits, where message bits were varying from M1 to M capital M. And remember that real valued energy signals we have confined to have a duration of capital T, and by Graham-Smith orthogonalization procedure, each of these signal SIT now can be represented by this equation, where Sij is the coefficient, okay, phi j is the orthonormal basis function. So, each and every energy signal we are representing by in terms of some coefficient and orthonormal basis function. Remember, this basis function is varying over 1 to capital N, definitely value of N will be less than capital M, and I, the symbols they are varying over 1 to available number of the symbols capital M. Each of these coefficients can be given by constructed by this equation. So, it is actually the original signal, the energy valued signal. If I multiply with the corresponding basis function and integrate it over the duration of the T, it will regenerate the each and every coefficient. And why this basis function? The property of this basis function is such that if I integrate two basis function of ith interval of and the jth interval, and integrate it over the interval of 0 to t, what is the symbol duration time, I will have the property that this integration value will give me equal to 1 if both are exactly same, and it will turn to 0 if it is not equal to 0, they are not, the instances are not same. What does it mean is this phi I and phi j telling that they will, the first condition that they will be 1, it is stating something like you are forcefully normalizing the power to be 1, and when it is 0, that means the second condition is signifying that they are perfectly orthogonal to each other. So, the property of orthogonality and property of normalization is there, and hence these basis functions are called orthonormal basis function. So, we are now interested to see that how SIT can be constructed given a set of Sij, and how Sij can be constructed given SIT. So, both of the generation mechanism are described in the next slide. Let us see. So, we know that if we are having a set of the coefficients from Si1 to Sin, and if we are having the basis functions orthonormal basis functions set. So, their corresponding multiplication with them and addition will generate my SIT following the expression shown in the last slide here. And oppositely, if I am having the incoming signal, the signal SIT, I will generate each and every coefficient by multiplying with the corresponding orthonormal basis function and integrate it over the symbol duration 0 to capital T, which is coming from the expression given in the expression here in the earlier slide, this one. Okay. So, the generation process is okay and understood clearly now. Now, with this understanding, that means we are now thinking that in a signal space we can actually represent any transmitted signal by combination of the orthonormal, by means of some orthonormal basis functions, and hence if I try to revisit BPSK modulated signal in terms of the discussion just now we have done, we understand that our transmitted BPSK modulated spread spectrum signal will be given as xt equal to pt into st. If I consider this st is the BPSK modulated signal which is spread by the sequence pt, st will be given by plus minus square root of twice Eb by Tb into cos 2 pi fct. Actually, the BPSK signal you need to transmit the signal value 1 and signal value 0. For that we need to transmit over the two real valued signal S1t and S2t. We transmit them in such a way that they are out of phase to each other. So, squared plus minus, so 1, if 1 is transmitted for the plus square root of twice Eb by Tb cos 2 pi fct, then S2t will be minus square root of twice Eb by Tb into cos 2 pi fct. Basically, two signals are 180 degree out of apart. Pi plus cos 2 pi fct will generate you the minus of the same thing. This analysis is based on the BPSK. So, here we are Pt into St will now lead down to plus minus square root of twice Eb by Tb Pt cos 2 pi fct. With the thought process should be aligned with the discussion that we have done, that in the signal space dimensionality we have two real valued signal associated with the BPSK transmission. And if I now define the orthonormal basis function associated with this BPSK transmission is given by square root of 2 by Tc cos 2 pi fct and phi tilde kt square root of 2 by Tc sin 2 pi fct over the duration of ktc to k minus 1 tc, means one chip duration, and if it is not existing anywhere, value is becoming 0, other case. You remember this cos and sin, they are perfectly orthogonal to each other, and hence they constitute the orthonormal basis function for representing the BPSK modulated signal here. We can reorient this equation 1.30 in such a way that we need 2 by square root of 2 by Tc. So, if I divide it by Tc and multiply the numerator and denominator by Tc and take square root of 2 by Tc into cos 2 pi fct out, and if I substitute that value by phi kt, I will be ending up with square root of Eb. N is coming what? N is equal to my g, which is equal to the bit duration by the chip duration. This is nothing but the gain. And Pt is now the summation of k is equal to 0 to n minus 1 pk, and because here we are considering the psi k is equal to 1 for the rectangular chip waveform. So, pk will be basically, and value of the pk will be either plus 1 or minus 1 continuously going on. So, the equation 1.30 will turn down to 1.31 for the bit duration period of Tb. If this is the condition for the St, then we will like to see that how many number of the orthonormal basis functions now we are dealing with. If I look inside the equation 1.31, see that as k is varying from 0 to n, so you need at least capital N number of the orthonormal basis functions to represent the value x t. So, which is not same according to the conventional communication system. There we were not requiring all this, because of spreading you are in the requirement of capital N number of orthonormal basis function to represent x t in the signal space. Come back to the jamming. For jamming signal j t, I have that jammer will jam me on both the incoming in phase on both the phases. So, jamming signal circuit will be phi k t plus j tilde phi k tilde t, and in both the situation we can recompute the value of this j k by the expression of this. Remember here one thing, jamming has no information about your it has the information about your bandwidth correctly, but it has no information about the phase. So, it does not know whether the signal is transmitted over in phase or only on the q phase. So, what he will try to do? He will try to load the power equally over the in phase as well as the q phase. And if as I am interested over the computation of the average power of the interference, jamming power it is. So, that jamming power will be always given by the square of this JT, the jamming signal, integrated over a duration of the bit, and utilizing the previous equation I can now write down it like this. Now, another thing is, as I have told that jamming has no information about your phase. So, he will load the equal power on the in phase as well as the q phase, and equating both of them, finally the jamming power is nothing but the twice of any one of this power that I have represented here. But interesting thing to note is that to jam, a jammer needs to spread his signal on the 2n orthonormal basis, because for him it is n number of basis functions is associated with the in phase, n number of the basis function is associated on the q phase. So, jamming is going on over 2n dimension, and signal is getting spread over capital N orthonormal dimension. Suppose with this understanding, let us enter into the coherent detector. Finally, this jamming signal plus ST plus JT is getting detected inside the coherent detector. Inside the coherent detector, if I see at the output of the coherent detector, we understand that inside the receiver, the received signal xt plus this jt, which is basically this st, it is not xt now, it will be xt for you, as we have seen that xt is equal to xt is given by my st into pt. So, you have received the spread signal xt. So, xt plus this jt in the receiver is now getting multiplied with pt. So, pt square it will be for the signal component, and but j part will be multiplied with the pt. And so, you are having inside the output of the detector, we will be always be seeing two different component, one is the contribution from the signal, one is the contribution from the jamming part. Signal part will be given by st into cos 2 pi fct, because p square t is equal to 1, and jamming part is having the pt associated with it. Now, if I proceed further, and we understand that the PSK signal, the discrete PSK signal is given by this that we have considered at the beginning, and if I substitute this value in the equation 1.38, st value if I substitute, and if I complete the integration, then I will see I will end up with this Vs is equal to plus minus square root of Eb, considering the fact that the carrier frequency is an integer multiple of 1 by Tb. And there also we won't consider the higher frequency terms, and for Bj, interestingly, if I substitute the value of now the Jk, we understand that it will be a summation, and Jt is there over an integration is running over a period of Tc. Now, if I utilize the integration of the jt and the jk, if I substitute from the previous equation, then I will finally end up here with square root of dc by dv. Please try to do this derivation by your own and please check whether you can come down here or not. Substitute the value of the jt and jk from the equations here. This is the value of the jk and this is the value of this jt, and substitute here and you will be coming down here. Now, if I see what is the random variable capital Vj, if I constitute the random variable Vj, where small vj is a sample value of that, and now it will be given by this pk into jk. Small pk is also the sample value of this capital pk. Now remember that this capital pk is a proportion that is coming from the pi, and its value to be +1 or -1 are equiprobable, and this probability is hence equal to half. And so, if we are trying to compute the pk into jk given the value of the jk, the mean value will be equal to 0, because this pk are equiprobable and the value of probability is equal to half. So, half minus half, it will give you the value. Half of the time the value is equal to +1 and half of the time the value is equal to -1. If we add up, we will end up with the mean value of 0. So, given the value of jk, pk into jk will always give the mean equal to 0. If I now constitute vector j, where actually j is the samples of the jamming signal starting from j0 to jn minus 1 over all n orthonormal functions, and given that value j, this random variable this vj, the variance of vj given that value of the j, now that can be computed as 1 by n square of this jk. And now I wish to refer the equation where we derive the value of capital J earlier. Recall the equation 1.37. Here we established that capital J is equal to 2 by Tb, that is the power, jamming power, it is equal to 2 by Tb summation of k running from 0 to n minus 1 jk square. We will utilize this equation in the next slide here to compute the value. See, here we understood that J, the total jamming power, will be equal to k is equal to 0 to n minus 1 jk square, and it will be also having a power of 2 associated with it, and this jamming power, let us go back, it has also it is a power. So, it has a component of divided by 2b, and if I substitute now in place of this, if you try to substitute, then you will be ending up with j into Tb by 2. So, this j into Tb by 2 and this capital N divided by n will be giving you the variance, and given the value of capital J, of course. And if I substitute the value of the capital N as Tb by Tc, you will be finally ending up with the variance of j Tc by 2. So, what is this? This is the approximate power that you are getting, the calculation of the power that you are getting at the output of the coherent detector after dispersing operation in the receiver contributed by the jamming signal. So, this is the power contributed by the jamming signal output of the coherent detector after dispersing operation in the receiver. Now, let us revisit. We have seen that output of the coherent detector, the signal component is plus minus square root of Av. We have seen it in the previous slide. So, the instantaneous peak power will be equal to Eb. So, the average signal power at the input of the receiver was Eb by Tb. This was the power computation, and output of the SNR, if I now try the output SNR at the output of the coherent detector, now it will be given by what? It will be given by this peak power divided by the noise. The noise is equivalent to my jamming power. So, I will divide JEB with JTC by 2. So, hence it is coming twice EB by JTC by 2. EB was the peak power of my signal at the output of the coherent detector, and JTC by 2 was the contribution from the jamming power at the output after dispersing operation and at the output of the coherent detector in the receiver. But what was the input section? Input section was, input SNR was EB divided by TB, that was the signal power input of the receiver, and it was also the jamming power was only J. If I the power became different because of the spreading operation only. So, the power at the input and the power that you are getting at the output, that is differing because the spreading has happened in for the jamming signal. If I now try to find out establish the relation between the output of the coherent detector at the output of the receiver and the input of the receiver, I will be ending up with the expression that the output SNR is a function of the SNR input to the SNR at the input of the receiver multiplied by 2 TB by TC. In the dB scale, the dB value at the output of the SNR will be the value of the input dB value, input SNR dB value plus the processing gain, because TB by TC is equal to the processing gain, plus 10 log to the base 2, we will give you the value equal to 3. Remember, this additional value of the 3 you are getting not because of the spreading, this is getting because you have utilized the coherent receiver. This is a because of the property of the coherent reception, you have got this extra value of dB value, but we are only interested here because of the spreading process you are gaining here the 10 log to the base 10 of the PG, where PG stands for the processing gain TB by TC. So, output will be some 10 log to the base 10 PG dB higher compared to the input SNR value. That is why we continuously was telling that output value of the coherent detector, you will have the higher value of the signal to noise power compared to the input of the input SNR values, and this extra value is contributed by the processing gain that was coming from the transmitter. Because of this gain, you will be able to see that if the conventional receiver, I have the plot of this signal to noise ratio, and I was suppose plotting the bit error rate where we are interested in. If a conventional receiver shows over the WGL channel that the 10 to the power minus 5 bit error rate, we are touching for BPSK transmission over a WGN as at 9.8 dB value. Then for this processing gain, based on the processing gain, you are computing the related value of TB by TC. Definitely, actually, to get that same 10 to the power minus 5 value, bit error rate value, you won't need actually to put that much amount of the SNR. You need to put a lower value of the SNR. You will automatically get the value that same is targeted 10 to the power minus 5 bit error rate value. So, this gain, the processing gain for a typical error computation or typical error rate, the gain is reflected, the processing gain 10 log to the base processing gain, it will be reflected over the gain on the x axis gain on the bit error rate graph or the performance analysis graph. So, how do we actually express the gain of this processing gain reflected on the system performance is like this, and this is true actually, and the gain, this gap with respect to the conventional communication system, it is not fixed, it is a function of this design of the sequence itself, because if you lower down the TC, the processing gain will increase and the graph will keep on proceeding, keep on actually coming like this, it will go towards the left and your processing gain will keep on increasing. But remember, whenever you are increasing the processing gain, somewhere you are having a some loss at the cost of something you are doing it. remember, whenever we are telling that we will be spreading the sequence, so spread spectrum is spreading the sequence, but remember we cannot spread a sequence beyond the available channel bandwidth. So, always the spreading is restricted by the bandwidth you are dealing with. So, whenever I am trying to have a higher spread, so the bandwidth that we are, the original bandwidth that we are trying to utilize, that bandwidth will be shrinked. So, more the value of the, lower the value of the TC you are starting with, more actually your bandwidth will be, there is no doubt about it, but the actual signal bandwidth that you are really getting, this with which actually we will start with, that will keep on shrinking. So, the message bandwidth you are going to be reduced, and the reduction of the message bandwidth that you are playing with will be a very big hit on the data rate that you are transmitting. So, increase in the processing gain will give you increment on the bit error rate performance. With lower value of SNR, you can get the same bit error rate compared to the conventional system, but the cost is that you cannot transmit the same data, the data rate of the transmission that actually is decreased. But however, with the almost of the same data rate, you need actually the higher bandwidth for the transmission. For the minimum data rate, whatever the, for the any kind of the data rate, whatever is the minimum bandwidth requirement, that for the conventional system, compared to that you are using a much more higher bandwidth to get the privacy or the message secrecy incorporated in the communication system. So, you are gaining in terms of secrecy, you are gaining in terms of the quality of the service, because in terms of the, there is a gain in terms of the SNR involved, but there is a very big hit on the data rate. Your data rate is getting damaged like anything. So, heavily fall will be there on the data rate. So, we will be ending here today with this concept of the jamming margin, and next class we will try to enter into the another kind of the frequency, another kind of the spread spectrum communication system, which is also widely used in practice, which is called the frequency hopping spread spectrum system.